It's my pleasure to introduce today's speaker. Shai is obviously no stranger to the CFA. After his PhD MBE, he then came here as an ITC fellow, then moved to Columbia as a Hubble fellow. Since 2016, has been an associate research scientist at CCA at Flatiron. Shai's largely worked with large cosmological simulations, looking at the origin of various properties of galaxies, ranging from how halos assemble through mergers and smooth accretion with Millennium simulations. He was on the teams behind both the Illustrious simulation and its successor project, Illustrious TNG, has used hydro simulations to study the origin of a wide variety of galaxy properties. I guess angular momentum we're going to hear a lot about today, the evolution of galaxy sizes, origin of metallicity galaxies and their dependence on environment, all kinds of stuff. And recently some very interesting work on the role of chaos in galaxy formation, which I guess we're going to hear a little bit about today as well. So without further ado, I shall over the show.
Okay, thanks so much. Thanks, Matthews. Thanks thanks for the invitation. It's really a pleasure being back here after a few years. Still feels like home, and pleasure having so many familiar and friendly faces in the audience. So what I'd like to talk about today is on the origin of angular momentum of galaxies, which is a field that has been something that has been investigated for maybe several decades now, and for sure I can tell you I don't have the bottom line, the final answer today, but I hope I can tell you about some new pieces in the puzzle. Okay, so I'll start with actually just one simple slide of introduction and motivation to the why is angular momentum interesting. So, and I'm going to talk about two things. One that has to do with more astrophysics, galaxy formation, one more with cosmology. So it's been observed that there is a strong relation between galaxy morphology and galaxy angular momentum. Of course, galaxy morphology, as we can see in this nice picture, it's maybe the most basic thing that we see when we look at the sky at galaxies. They come in a great variety of shapes, sizes, colors, and morphologies. And in particular, of course, we have the Hubble classification scheme that distinguishes between two main classes of ellipticals and disk galaxies. And it's been found that these, and we really want to understand the origin of this. And it's been found that there is a strong relation between the morphology and the angular momentum content of galaxies. So angular momentum being a physical quantity, a conserved quantity, I think gives us a good way to try to approach this question of the origin of galaxy morphology diversity. Specifically what this relation looks like can be seen here on a plane of the specific angular momentum of the stellar component of galaxies versus the stellar mass, where we have disk galaxies in blue here and ellipticals in red. So first we see a scaling of the specific angular momentum, specific being angular momentum magnitude over stellar mass, scales as the stellar mass to the 2/3 roughly, which we can see here. And also there is a significant separation, dependence on the galaxy morphology type, so that we have two kind of parallel relations. The second line of motivation for why looking at angular momentum is that this can actually help us for cosmology. So one way we can approach, try to measure the cosmological parameters is through weak lensing, cosmic shear surveys, which probe how galaxies, how the shapes of galaxies correlate on the sky. And this has to do with, of course, how the galaxies are oriented. Now, this is important both for elliptical and for these galaxies, but in particular, the assumption is that for these galaxies, the way we see the galaxy oriented on the sky is related to the direction of its angular momentum, because these galaxies would rotate in a plane perpendicular to their angular momentum. What this plot shows is inference for a mock Euclid-like survey of the cosmological parameters when there is no effect of intrinsic alignment. So when galaxies are not intrinsically, the directions of galaxies on the sky are not intrinsically correlated with one another. So this is the middle points here, and their error bars that you would get in cosmological parameters. But these other points, the yellow and the red points here, would be the inference on the cosmological parameters if you had a survey which was actually affected by intrinsic alignments of galaxies, but you didn't include them in the model. So you would get biases, in particular on parameters like omega m and sigma, omega matter and sigma. So we'd like to build informed models for how galaxies correlate, shapes of galaxies correlate on the sky. For that, we need to know their angular momentum. Okay, so we'll dive right into the basics of what sets galaxy angular momentum. And the basic theory is called tidal torque theory. It's pretty old, and it says the following: in the linear growth phase of density perturbation in the universe, the angular momentum is proportional to the tensor of inertia of a protohalo of a region in space that will eventually collapse to form a halo. So it's just the inertia tensor. This factor here is deformation, or the traceless part of the deformation tensor. So we call it tidal or shear tensor. It's simply the traceless part of the Hessian of the initial potential. And we have the asymmetric, antisymmetric symbol here that collects different terms from these two factors here. And we'll talk a bit about what this means. So this is basically what the angular momentum in the initial phase is proportional to, and then it grows over time like this, which in an Einstein de Sitter universe is simply proportional to cosmic time. So essentially what we have here is that the large-scale structure applies torques on the inertia tensor of the region that will collapse into a halo.
So Shai, this assumes a monolithic collapse of, of a region, like the spherical collapse. But in reality, you have mergers that could give a lot of angular momentum to the merger product.
Right.
And that is not dictated by tidal torques, but by the orbit of the merging components.
So the orbits of the merging components itself its origin is from the tidal torquing on those components from the larger scale. So I'll talk a bit, just in a bit about how indeed non-monolithic, in what way this is a simplified monolithic picture is incorrect. But this is a good point to stress that mergers are naturally included in this picture, because what we're talking about, this inertia tensor, is of everything that will in the end be in the final galaxy, including all the subcomponents that merge around. Okay, the assumptions, just quickly going through the assumptions that go into deriving this form. We assume there's a Lovich approximation. That means the perturbations grow in the linear phase. The positions of particles are essentially their initial positions plus some displacement field that is proportional to the gradient of the potential. Then this is in leading order in perturbation theory, which is second order for the angular momentum. And then we finally assume that this growth over time continues in the linear phase, but at some point around the turnaround time of the halo, this protohalo decouples from the environment. This large scale torques are not able to, as the halo collapses, they're not able to really apply significant torques. And so after something like the turnaround time of the halo, we have conservation of whatever angular momentum was gained in this linear phase.
So what criteria do you have to define the boundary of the protohalo versus its environment?
Yeah, so so what we're saying here is that this assumes that we know what is the protohalo. So we just look at this, the region in space that eventually will be inside the halo. Determining in the initial conditions what that region is complicated. We don't really know.
Just a quick question. So we're looking really at the effects of gravity. Is there any role that magnetic fields would play? Because you could imagine that locally, through turbulence or other processes, they are being influential, say, near the center of galaxies, and that although they may not be the main drivers, they may affect things like warping and orientation.
Yeah, so I'll talk in a bit about
Not the dark matter. Not for the dark matter.
Yeah, so, right.
Dark matter carries gravity.
So there are very important effects that differentiate this evolution for the gas from the dark matter. But in this simple picture, the flow, the initial flow in the linear phase is completely laminar. It's just the Lovich approximation, and the gas just follows the. So there is no initial turbulence. It's been smoothed out by the expansion of the universe, and the gas just simply follows the dark matter. It's the simple picture, but we'll talk about deviations from this picture. So just to briefly go through a few implications, properties of the angular momentum of protohalos in this picture. So one is that due to the de Civita symbol here, the angular momentum arises due to misalignment between these two components, between the inertia tensor and the large-scale tidal field. If they were perfectly aligned, you would get no rotation. In practice, what one finds in simulation is that actually they're pretty well aligned. So it's just the distribution of the cosine of the angle of these two components. So this is a small deviation from alignment of these two components that gives the angular momentum. We can also expect to get correlations of angular momentum between nearby halos, because nearby halos, while they may have different inertia tensors, they will be affected by the same or similar large-scale tidal field. So this gives us some idea that we might expect some intrinsic alignment of galaxies. Another curious, interesting thing to note is that the angular momentum is exactly zero in the linear phase within spheres. This is because the initial field is curl-free. So if you integrate within a sphere, you get